Okay, so now we've learned how to determine what the dimensionless pi terms are. Now, what on earth do we do with those? So now, what do we do with the pi groups? So, and that is, we determine that pi 1, and this is one that has that contains the quantity of interest, is equal to some function of pi 2 and pi 3 and all the way to pi n minus k. Okay? And so how you actually use these numbers, if you're doing experiments, is you set up the experiment such that pi 2 of the model, which is your experiment, and is equal to pi 2 of the real object. And so this is real. Okay, and then you need pi 3 of the model, which I'm just going to call m, is equal to pi 3 of the real object. Okay, and so forth, all the way on to the last pi group, pi n minus k for the model, is equal to pi n minus k for the real object. Okay, and so if you've carefully chosen your experimental conditions such that pi 2 for the model is the same as it is for the real object, pi 3 for the model is the same as it is for the real object, and the last pi group for the model is the same as it is for the real object, then you are guaranteed that pi 1 of the model is equal to pi 1 of the real object. And remember, pi 1 contains the quantity of interest, like the drag force or some other thing like this. So in other words, you choose the experimental conditions based on pi 2, pi 3, and pi n minus k. And so these tell you how, or I should say, these provide conditions to set up the experiment. Okay, so you can use these extra pi group, or you can use these pi groups here to determine what the height is of your scale model, what flow velocity you need, what type of density do you need, things like that for the fluid. Because the fluid going around the object, such as an aircraft or something like that, you may use a different fluid to test it in the experiment. For example, it's occasionally useful in studying drag on an object, say in a somewhat high-speed air, but not supersonic or anything like that, to test it in water, just because sometimes that's more practical, and sometimes for drag on an object in water, it's more practical to test that in a wind tunnel. Just due to the fact that it's easier to get the pi terms equal together. So the fluid that you use in the experiment does not have to match the fluid that's used in the real world. In fact, sometimes you must change the fluid in the experiment. And so I'm going to give a little example here. So example, we have the strut on a bridge that looks something like this. It's of height d and of length h. Okay, and there's air flowing into it, at some free stream velocity v, and that's equal to 50 kilometers per hour, and it's air, and the viscosity is equal to 1.79 times 10 to the minus fifth Pascal seconds, and rho is equal to 1.23 kilograms per cubic meter. Okay, and D equals 0.1 meters and H equals 0.3 meters. Okay, and oops, I'll move these because they're in the way. And so what the experiment is measuring is that you guys can Google this. There's a famous bridge failure called the Tacoma Narrows. Where on a very windy day, the bridge started shaking due to high-speed winds, and the bridge literally got into a resonance due to the wind, and it shook itself apart. And so when they test bridges, they need to make sure that doesn't happen. And so fluid mechanically, what happens under certain flow regimes is that the streamlines just don't go over and around the object like you would imagine, is that the flow actually oscillates back and forth. And so the streamlines will look something like this. And it'll go up, then the streamline will go something like this. Okay, and in these little troughs here, there are pairs of counter-rotating vortexes. Okay, and essentially what these vortexes do, and basically what this shaking set of streamlines does, is it applies a torque, it applies a shaking torque on the object. And if this frequency of these vortices is in the proper regime, this torque can become quite large, and it can couple with the bridge, set up a resonance, and you'll learn all about that when you take vibrations, and the bridge can literally shake itself apart, which you obviously don't want. And so there is an oscillation frequency omega. And so if you're a bridge designer, you really want to know what omega is as a function of say the wind speed and the design of your strut. And so some of these things are so sensitive, even though you can compute them using computational fluid dynamics. And in certain scenarios, you are mandated almost by law by the safety boards that you have to do experiments. Okay, and so what they're going to do, or what they're going to do for the model, a test model, is the bridge is too large and the flow is too high to use it practically in a wind tunnel. Although in the problem setup, it's actually not that bad. But you could think of a bridge strut would be rather large to put in a wind tunnel, so you need to shrink it down a little bit. And so for the model, we're going to choose the height D for the model. I'll call that dm to be 20 millimeters, which equals 0.02 meters. And we're gonna and in the model, which is going to be a smaller, which is going to be geometrically similar to the real strut, we're going to choose the test fluid to be water, where rho is equal to 998 kilograms per meter cubed, and the viscosity equals 10 to the minus 3 Pascal seconds. Okay, and in this experiment, omega of the model is measured to be 49.9 hertz. And so what we are asked to find is, first, what was the velocity of the water that the experimentalists used, of the H2O used in the experiment? What is the length, HM, of the model? And what is the vortex frequency, which is causing the oscillations of the real object? So essentially what we're doing here is, it is impractical to put this whole thing with real air in a wind tunnel. So instead, we're going to use a smaller version of this and place it inside of a water tunnel. And then we're going to set it up such that the pi groups for the model or for the object are the same between the two experiments. Then with the experiment, you measure the shedding frequency or the vortex frequency of the model, and then you can go and map that, and that will tell you what the vortex frequency is for the real object. And then you can feed, and then if you're the fluids engineer on this, you can give that information to the structural mechanics people, and they will put that into their models and determine whether the bridge is going to shake itself apart or not. Okay, so where do we begin? So first, we need to use Buckingham pi, and we need to make a load of assumptions on what this frequency is going to be a function of. And we're going to assume that that the experimentalists were smart, and the model is geometrically similar. Okay, and we'll assume that the shedding frequency is a function of d, h, which d and h are just the geometry of the object, the incoming flow velocity, the density of the fluid, and the viscosity. Okay? And so we will assume that. And so the solution, you use pi theorem, and to find, and I'm not going to go through the details on that, but note, if you want to do that for your own exercise, omega has units of hertz, which is time to the -1 power. But if you use pi theorem and you don't make a mistake, what you'll find is that omega times d over v is equal to a function of d over h and the Reynolds number rho vd over mu. So this is the Reynolds number. Okay, and this is a geometric parameter. And this parameter here is called the screw hole number. Okay, because the screw hole number, oops, wrong one. The screw hole number appears pretty commonly in these types of scenarios, and the Reynolds number is a number that you're going to get to know very well here fairly quickly. And so with this, we have pi 1, which contains the quantity of interest, equals omega d over v. Pi 2 is a geometric parameter, which is d over h. And pi 3 equals the Reynolds number, which is rho Vd over the viscosity. And so, for pi 1 of the model to equal pi 1 of the real object, we need to set up the experiment such that pi 2 of the model is equal to pi 3 of the real object. Oops, not pi 3, pi 2. And pi 3 of the model is equal to pi 3 of the real object. Okay, and so now we're going to go through and find and determine in the experiment if pi 2 is equal is the same between the model and the experiment, and then set up the experiments such that they are equal. So now let's first look. So first let's work with pi 2, and so pi 2 equals d over h, and we need pi 2 for the model equal pi 2 for the real object. So this implies that d of the model times h of the model, which is pi 2 of the model, is equal to d over h. So this is equal to pi 2 of the real object. Okay, and we know d, we know h, and we know dm. And what we're trying to find is hm, so we just solve this for hm. This implies that hm equals h times dm over d. Okay, and if we stick in the numbers, we find that hm equals 0.3 meters, which is h, times 0.02 meters over 0.1 meters, or hm equals 0.06 meters or 60 millimeters, whichever you prefer. Okay, so pi 2 gave us information on what to set hm to be. Okay, and that's just a geometric parameter. That's saying that the height to the width ratio of the test object needs to be the same between the experiment and the real object. And now we have pi 3, and pi 3 is equal to pi 3 is equal to the Reynolds number, so that's rho Vd over mu. And we require that pi 3 of the model is equal to pi 3 of the real object. So this implies that rho of the model, v of the model, d of the model, mu of the model is equal to rho Vd on the actual object. And we know rho, we know v, we know d, we know mu. We know mu of the model, we know d of the model, and we know rho of the model, and we don't know the velocity used in the experiment. And so you can use pi 3 to determine what velocity you need to use in your experiment to ensure that your measurements are consistent between the experiment and the actual object. Okay, and so we solve this for v. This implies that v of the model is equal to v times d over d of the model times rho over rho of the model times the viscosity of the model fluid over the viscosity of the actual fluid used on the real object. And so if we stick in the numbers, that equals 50, that equals 50 kilometers per hour times 1,000 meters per kilometer times 1 hour per 3600 seconds times d over dm, so that's 0.1 meters over 0.02 meters times rho over rho m, and that's 1.23 kilograms per meter cubed divided by 998 kilograms per meter cubed. And this is multiplied by mu m over mu, and that's 1 times 10 to the minus 3 Pascal seconds divided by 1.79 times 10 to the minus 5 Pascal seconds. Okay, and then this gives us, first of all, V equals, V of the air is equal to 13.9 meters per second. And Vm, what we set the velocity of the water to is 4.79 meters per second. Okay, and so what this is saying is that to get good measurements here, you don't just take your scaled down object and toss it in a wind tunnel that has the same air at the same velocity. You will not get a comparable quantity of interest out of this. So now we know pi 2 and pi 3, which is pi n minus k for here, are the same between the model and experiment. Okay, thus pi 1 of the real object equals pi 1 for the model. Okay, and this means that omega times d over v is equal to omega of the model, d of the model, over v of the model. Okay, and we know v of the model, we just calculated that. We know d of the model, and in the experiment we measured the frequency of the model, and we know the wind velocity, and we know the size of the real object, so we can solve for omega. And omega equals omega that you measured in the experiment in the water tunnel times v over vm times dm over d. And if we stick in the numbers, omega equals 49.9 hertz, which is what was measured in the water tunnel, times 13.9 meters per second divided by 49.9 meters per second. It's not 49.9, it's 47, it's 4.79. 4.79 meters per second times 0.02 meters over 0.1 meters. And this implies that omega of the real object, based on the experiments and the similarity, is 29 hertz. Okay, and so this is how these pi groups are actually used. And so in these experiments, you need to match all the pi groups of pi 2 through pi n minus k. If those are the same between the model and the experiment, then the pi group that contains your quantity of interest is also the same. And now, as a caveat, so that's what you do if you have 2 or more pi groups. Now, what if there is only one pi group? Right, so what that means is that we have f of pi, and only pi 1 is equal to 0. Well, we do the thing, this obviously contains the quantity of interest, so we do the same thing, where before, if we had 2 pi groups, you would have f of pi 1 and pi 2 equals 0, or pi 1 equals some function of pi 2. Okay, well, we do the same thing over here. And we have pi 1 equals some function. And well, there is no pi 2 over here, so it's an empty function. It's a function of nothing. Okay? And so there are no pi variables left. And so it's a function of nothing. And a function of nothing is a constant. Okay, and so if there's only one pi group, this is equal to a constant. Okay, so if only one pi group, then that pi 1 is equal to a constant. Okay, and you will see this from time to time. Okay, so as an example, in a certain regime, the drag on a very slowly moving sphere is the drag force is equal to a function of the diameter of the sphere, v, and mu. Okay, and in this regime here that I'm talking about, it's actually called creeping flow. And here the streamlines just actually hug. Here in this creeping flow regime, the streamlines actually hug the object for the entire way around, but this only occurs for extremely slow moving flows. And for everyday objects, you almost never have creeping flow. But if you have an extremely tiny particle, like on the order of 1 or 10 micrometers, it's very easy to have creeping flow conditions. Okay? And so if we apply Buckingham pi, I'm not going to show you how to do that because we've done plenty of examples. That will give n minus k equals 1. So there's only one pi group, and that pi 1 group equals the drag force over mu v d. So because there is only one pi group, we can conclude that d, or the drag force over mu v d, is equal to a constant. Okay, and so you would need to set up the experiment to measure that constant, and that would work for a lot of different scenarios. Okay, and okay, so now we talked about cases where you have one pi group, cases where you can achieve full similarity between all of the other pi groups, and what if it's not always possible for all of the pi groups to achieve similarity between all of the pi groups? So what if it is impossible for pi 1 equals some f of pi 2, pi 3, pi n minus k, and again pi 1 contains the quantity of interest. What if I guess full similarity requires pi 2, pi 3, all the way to pi n minus k be identical between the experiment and the real object. Okay? But sometimes it's not possible to do that. So, but this is not always possible. Okay, so the reason being is that maybe you can match, say, pi 2, but if you match, say, the velocity condition determined by pi 2, then then you need pi 3 to determine a density, which is going to determine the fluid in the experiment. Well, sometimes you may require, if you actually go through the calculation sometimes, that may require a viscosity of, say, 10 to the 10, I don't know, I'm just coming up with a crazy number, Pascal seconds, a density of 10 to the minus 4 kilograms per meter cubed, or a temperature equal to, say, 1000 Kelvin, or maybe even larger, let's say 3000 Kelvin. Okay, and so sometimes to match all of the variables, to match all of the pi groups between the model and experiment, it requires a crazy unphysical viscosities, densities, or even temperatures. So, for example, maybe to match the density, or to match the Reynolds number, if the Mach number is going to determine what the velocity is, you can use the density or you can use the temperature to change the density of the incoming air, and maybe you need 3000 Kelvin. Well, that's not practical. You're probably going to start melting things, and that's just not practical. So it's not always possible to achieve full similarity between all of the pi groups between the experiment and the real object. Okay? And so when this happens, it's called incomplete similarity. Okay? And so, and also in addition to the pi groups, full or complete similarity between the experiment and the real object requires 1, geometric similarity, and that is the model and real objects have the same shape factor. Okay, and the sizes are all scaled by the same factor. Okay, and that's called geometric similarity. And sometimes it's not practical to achieve full geometric similarity. So say your real object contains, I don't know, it looks something like this, and there's a little crevice. Well, when you scale that down to the experiment, your object may be physically this big, and this crevice, oops, I drew it wrong, and this crevice is too small to make. Okay, so in that case, you're probably not going to be able to achieve full geometric similarity. And so in those cases, you essentially just have to accept that there's going to be some error or uncertainty between the experiment and the real object due to that. Or maybe there's a small little strut sticking out like that. Well, in the real object, that would just be a tiny, skinny little needle that would probably break off. And so sometimes it's just not practical to achieve full geometric similarity, and you just have to accept that as an error. But in general, the shape factor, that is the H and the L, need to be, is that they need to have the same ratio between the real object and the test object. Okay? And then there's kinematic similarity. Okay, and what this means is that the velocity at any point in the model has a magnitude scaled by a constant factor. Okay, so basically what that means is that if I have, say, the streamlines over a circle, is that I choose a flow regime and the flow condition in the experiments such that in the experiment I have streamlines that are actually identical in shape. It's just that the velocity in their shape is just scaled down in size. Okay? But they have the same direction and everything else. So the streamlines are geometrically similar. And V of the model here equals some scaling factor times V of the real object, and the velocity, say here, V of the model at say a V of the model at this location here is equal to the same scaling factor times the velocity of the model at that object. So the velocities are basically slowed down or sped up by the same factor everywhere. Okay, and another aspect of this is that the flow has to be in the same regime. Okay, so for example, if you want to measure the drag on a supersonic sphere, say you have a flow with the Mach number, say a Mach 5 flow going over a sphere, and you have a shock and a velocity v going in, well, you can't put this in a water tunnel and measure the drag force on this object, because if you put in a water tunnel, the flow will be subsonic and the shock won't exist. And for these types of for these types of flow conditions, the shock in just the type of the flow regime has a huge influence on the measurements of the experiment. So that's just one example. So if you have supersonic flow going over the real object, you need supersonic flow going over the experimental object. Okay? Another example is that if you have cavitation, so you need supersonic flow in real and experimental objects. Okay, or if it's subsonic, there are all kinds of other conditions that apply for different flow scenarios. If there is no cavitation in the real object, say you're measuring drag on a sphere in air, and you stick it in a water tunnel, you need to make darn sure that there is no cavitation in the water tunnel. Okay? So, in other words, if you are measuring the drag going over a sphere, and by plopping it into a water tunnel, you have to ensure that there will be no cavitation of the water as it goes over and around that object, which can happen, or for a pump or something like that. And similarly, another thing that can go wrong is sometimes you want to measure the drag force or something like that on an extremely tiny sphere, like a tiny little particle. So, for example, if the object is tiny, and by tiny I mean the diameter is on the order of 100 nanometers, so extremely small, well, here this is a non-continuum. Remember, I talked about that in the beginning of class, and essentially what that means is that you can actually physically count the molecules. You know, you need a computer to do it, but the molecules impacting the tiny sphere are countable. And this is called a rarefied flow regime. And essentially, if you want to measure the drag experimentally on this extremely tiny particle, because it's so small, and all the continuum stuff that we've been using throughout this entire class, those are no longer in play. So you can't just take, you can't do an experiment, cannot do experiment of a larger particle in a water tunnel. Okay, because you've completely changed the regime of flow. Okay, so kinematic similarity requires that the streamlines are geometrically similar, the flow velocity at any point is scaled by the same factor everywhere in the flow, and that you are in the same flow regime. That is, if you are measuring a subsonic or the drag on a subsonic airplane, in the wind tunnel it must be subsonic. It cannot be supersonic. If there's cavitation in the real object, there must be cavitation in the experiment, and a whole host of other things. Okay, and then there is dynamic similarity. So the third requirement is that there's dynamic similarity. And that basically means that the force distribution is similar. Okay, and so I'm going to wrap up the discussion on similarity pretty quickly, but before I do that, I'm just going to list the common dimensionless groups. And there are probably literally hundreds of these. But the most common one, and one that you'll be using in chapters 8 and 9, is the Reynolds number. Okay, and that's given by rho v L over mu, and L is just a reference length. Okay, and for a sphere, that reference length would be the diameter, and we'll get more into that. And in general, that's given the symbol Re, and it's a ratio of the inertia forces over the viscous force. Okay, and so the inertia force is sort of given by a rho v, and the viscous force is representative of the viscosity. Okay, and there's a more formal way of actually showing that, but in this class I'm not going to do that. And there's a Froude number, and that is equal to V over square root of GL, and that's given by the symbol FR, and that is heuristically the inertial force over the gravitational force. Okay, but I don't like that description of it, because what the Froude number is this is the wave speed of a shallow, not wave, this is the speed of a shallow wave in a liquid. Okay, so and so in other words, if you have, say, a lake and there's a ripple on the surface, and that's going to move at some velocity v wave, and that v wave is equal to square root of g times L. And L is typically the depth. Okay? And so really the Froude number is the ratio of the speed of the water to the speed of the surface waves. And the Froude number in folks who work with the fluid mechanics of rivers, like in the civil engineering department and things like that, the Froude number plays the same role in those types of flows that the Mach number does for fully compressible flows. And so then I might as well discuss the Mach number. That is given by V over, I did the square root, V over A, and A equals square root of K RT for ideal gas. Okay, and that's the Mach number, and that's given by the symbol M. And that's just the ratio of the fluid velocity to the sound speed. Okay, and there's an Euler number, and that's by P over rho V squared, and sometimes you see a 1/2 there, but not always, and that's given by the symbol EU, and this is really representative of the pressure over the inertia. Okay, and there's the Struhel number. And that's defined by the shedding frequency, which we just went over in a little problem, times a reference length over the velocity, and that's given by the symbol ST. And if you have a flow that's dependent on surface tension, you can check if that's important by using the Weber number. And the Weber number is defined by rho v squared times a reference length over the surface tension, and that's given by the symbol WE. And that's really that's representative of the inertia force over the surface tension force. So if you have a flow and the Weber number is small, surface tension is important. Okay. And so there are a lot of these common groups and parameters, but by far the number that you're going to be using the most often in this class, and you'll see it in all the time in heat transfer and fluid mechanics and all sorts of places, is the Reynolds number. And so that ends the chapter 7, and we're going to, the next chapter we will do is chapter 8 on pipe flow.